Hey guys, Mr. Backberg here. In this video, we're going to look at modeling growth with other bases. So we've seen it happen a couple different times where the differential equation dy dt equals k times y has led us to the exponential solution y equals y sub 0 times e raised to the kt power, where that y sub 0 is your value of y at a time of 0. We could also rewrite this solution using a different base. So we could rewrite it in the form y equals y sub 0 times b raised to the ht, where b is any positive number other than 1, and h is a different rate constant, but it's related to k using the equation k equals h times the natural log of your base b. So this means that we can take exponential growth problems and we can model them using any positive base as long as that base is not 1. So we can choose a convenient base to fit a given growth pattern that we're dealing with. So in this example, we're going to look at using a base that might be convenient based on the context of a problem. So at the beginning of the summer, the population of a hive of bald-faced hornets, which are actually a type of wasp, is growing at a rate proportional to the population. Starting at a population of 10 on May 1st, the number of hornets grows to 50 after 30 days. If the growth continues to follow that exact same model, then how many days after May 1st is the population going to reach 100? Well, one important thing in here is that we're saying that the rate is proportional to the population. So that lets us write out an exponential growth model. So we're using something that's going to look like y equals that y sub 0 amount times b raised to the h times t. Now we know that our y sub 0 initial amount, well, we started with 10. So we're going to do y equals 10 times. Now as far as the base goes, here's what happened. We know that our population grew by a factor of 5. It got 5 times as big after 30 days. So for our base, we're going to use a base of 5. And then for that h value, we know that this happened after 30 days. So what we're actually going to do with that h value is we're going to use 1 over the time frame that we're looking at. So we're looking at 30 days, so we're going to do 1 over 30, and then this will be times our t. Now using this equation, we're going to use that equation to try to figure out when we hit that population of 100. So that y value on the left-hand side, we're trying to figure out when we hit 100 using this equation that we just wrote out. So the first thing I'm going to do, we've got that 10 times this 5 raised to the power happening. So I want to get rid of that 10 by dividing both sides by 10. So then we're going to have 10 equals 5 raised to the power 1 over 30 times t. Now we've got a little bit of an issue because that t is up as a power on that 5. So what we're actually going to do is take the natural log of both sides. So then this will say the natural log of 10 equals the natural log of 5 raised to the power 1 over 30 times t. And then what we're going to do is use a property of logarithms. One property of logarithms says that if you're doing a logarithm of something being raised to a power, you're allowed to take that power and drop it down in front of that logarithm. So then we'll have the natural log of 10 is equal to 1 over 30 times t times the natural log of 5. Now our goal is to isolate t, so the first thing I'm going to do is divide that natural log of 5 over to the left-hand side. So this will say the natural log of 10 divided by the natural log of 5 is equal to 1 over 30 times t. Now to get rid of that 1 over 30, I'm actually going to multiply both sides by 30. So then this will say 30 times the natural log of 10 divided by the natural log of 5 is equal to our t value. Now we should be able to type that whole left-hand side into our calculator. And if we do that, going out to 3 decimal places, we're going to get 42.920. So we can say that approximately 43 days after May 1st, our population is going to hit 100. Now in this example, we're going to look at using carbon-14 dating. So scientists who use carbon-14 dating use 5,700 years for its half-life. We want to find the age of a sample in which 10% of the radioactive nuclei that were originally present have decayed. So we're modeling this using some sort of equation that says y equals y sub 0 times b raised to the ht power. And we're going to approach it similarly to how we approached the last one. Now, we don't necessarily know our initial amount, so I'm going to leave that as y sub 0 for right now. But as far as that base, we're talking about the half-life, so I'm going to use a base value of 1/2. Now, for our h, we said that we were going to do 1 over the time frame that we're talking about, and the half-life that we're using is 5,700 years. So I'm going to do 1 over 5,700 times our t value. Now, as far as that y value on the left-hand side, on the previous example, we knew that we were trying to hit a population of 100. Well, here, we don't necessarily know what number we're actually trying to hit. We just know that 10% of the material has decayed. But here's what that's going to tell us. If 10% has decayed, then there's 90% of it left over. So we have 0.9 or 90% of the original sample left. So 0.9 times that y sub 0 value, and that's going to equal our y sub 0 times our 1/2 raised to the power of 1 over 5,700 times that t value. Now we're solving for t this time, so what I'm going to do is divide that y sub 0 over to the other side, and that's going to cancel out. So we have 0.9 equals 1/2 raised to the power of 1 over 5,700 times our t value. Similar to what we did on the last example, we're going to take the natural log of both sides to help us deal with that exponent. So the natural log of 0.9 is equal to, I'm actually going to drop that power down right away. So 1 over 5,700 times t times the natural log of that 1/2. Now I want to get t alone, so I'm going to divide that natural log of 1/2 over to the other side. So we've got the natural log of 0.9 divided by the natural log of 1/2 is equal to our 1 over 5,700 t. But then I'm going to multiply that 5,700 over to the left-hand side. So 5,700 times the natural log of 0.9 divided by the natural log of 1/2 is equal to our t value. Now we should be able to type that whole left-hand side into our calculator, and if we just approximate in here, we're going to get right around 866. So we can say, based on the work that we just did, that our sample is about 866 years old. That's going to be it for this video. Thanks for watching.